All right, so then let's do share the screen. Okay, so what we are doing is now we call the infinite series, or we call it series, right? So when we call series, it's always infinite. Okay. And what we call a series is a, say, it's an infinite sum. Yes. So series is of this form. And so sometimes you start with one, dot, dot, dot. Okay. So there's always infinite summations. So in our terminology, series is always uh, infinite summations. Okay. Sometimes we write it down as sigma. Now we use the sigma notation again. So 1, 2, n. Okay. Okay. So how we make sense of this infinite summations, because we won't be able to complete the summations simply because there's infinite terms. Okay. So how to say this is converged or not? Okay. So what we're doing here is just looking at the series partially. What do you mean partially? Okay. So here it is the partially we mean something like this. 3 dot 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 say a n 4. Okay. And look at the finite sum. Uh, you consider the finite sum. So S1 is equal to A1. Why S? Because it's sums. Okay. S2 is A1 plus A2. Okay. S3 is A1, A2, A3. So in the same fashion, Sn is just the sum, dot, 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 till A. Okay. And we consider this, now it is a series, sorry, a sequence. S1, S2, S3, S4, sorry, just to make it different from A. Okay, so this is called sequence of partial sums. Okay. So now what we consider as the convergence. Well, convergence means that the converge or diverges, being convergent or not, okay, of the series is the same as the convergence of the sequence. Let me write down. of the series as the convergence of the partial sum. Okay. Hmm. 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 Convergence is okay. So this is how we define it. Uh, we say the series. Now this is the infinity. Converge or diverge if of partial sum convergence or divergence. Okay, let's do some example. Let's start with the one that we had. Yes. Uh, um, so this is the sum of a from 1 to infinity. 1 over 2 to the, say 1 over 2 to the, say from 0. Okay. So this is just 1, 1/2. I should write something like this, 1/2. All right. So let's see the partial sum. Partial sums is just S. This is A0, A1, A2, A3. Oh, yes, start from 0. Okay. F1 is just uh, S2 is just 1 plus 2 square. Okay. And then Sn is just the 1, 2 square to the n. Okay, so this is partial sum. Let's check this out. We can uh, we know how to compute this one explicitly. So let's go back to this one later. We do this one first. We know from the previous formula, if you do this kind of summations, uh, you can start from 0, from 1, it doesn't matter. So from 0. R over r to power of k. That means r. All right. You see, this is the formula that we computed earlier. This, if you Okay, you know this trick, same trick. This one here. Yep. Okay. So then that's the formula. So we know the partial sum should be just one half. You know this is uh, of course you can compute this. This is still easy, but we know this one is one minus 2 to the n plus 1 over 1 minus 1. Okay, so this is 2 of this. So from here, as n is just uh, 2 times, this is 1 half. Oh, sorry, this is wrong. This is 1 half. Because r is 1 half here. Okay. And we can compute that. So how does Sm converges? Converge. All right, so let's compute the limit. Limit n goes to infinity of this Sm is just this limit. Yeah. 2 times 1 minus 1 half to the power n plus 1. All right, because 1 half is a fraction less than 1, if you keep adding the exponent, the power, then it will just go, it keeps smaller and smaller. So just 1 half, 1/4, 1/8, 1/16, 1/32. This goes to 0. As this goes to 0, then it's just 2. Okay, so we say that this series uh, 1 half I should say this is an. Let me rewrite. This should converge with limit, or we call it sum, 2. So we say in this case, okay, is actually this limit. And right? Yeah, this is a partial sum. Okay, questions? Okay, later on we will do something like this. We can express sine x as a sequence. Exponential is the sequence. Okay, so that's the idea. Okay, so this is the partial sums and partial sums. Okay. This is definition of the convergence of a infinite series. All right, so let's do the what we call a geometric series. Well, a geometric series is a series of this form. Uh, now, let's see. I just write this down as A times R is a constant. Okay. A and R is constant. R is called ratio. Okay. So in this case, this is our model actually, partial sum. Okay. So this AR plus AR square until AR to the N. Okay. So you can write this down, take the A out. So you back to this partial sum of R. Okay. And you know that this is has formula 1 minus R to the N plus 1. 1 over, yeah, R over 1 minus R. There. And R. This has limit if, all right. So if R is bigger than 1, absolute value, uh, adding the power and just make it bigger. Okay. And if the power, sorry, if ratio is less than 1, absolute value, then it's getting smaller. Convert to 0 if and see. If R is 1, R, and it is, say, divergent if R equals, say, I should say, what if R is negative 1? R is negative 1 is divergent, or R is bigger than. Okay. All right, so this is why this is the reason. This converges to is converged to 0. That's the one. Okay. So then this is the formula that you know from high school. The limit of convergent series. Okay, so that's the reason we have this. Okay, is one. Sorry, this is A. If absolute value is less than 1. Okay, and divergent for is bigger than 1, equals to 1. Okay, so let's take a problem. Geometric series. All right, for example, this one here. I just show you this. Won't write this down. 4/3 for 4/9, 4/27 for this one here. Okay, so you see, this is, you can take 4/3 out. 4/3 out, and you get 1. How you get 4/9? So this 1/3. Okay, so this is 4/3 out, so 1/9. Okay, so in this case, A, this is A. This is A. This is R. Sorry. This is R. Okay, so this confers to 4/3. 1 minus 1/3. Okay, so 4/3 over 2/3, so that's 2. What we have. So we won't do this geometric, but we'll show you this one here. So this one. Express write this down as a repeating pattern. Okay, what's this mean? Repeated factor. Not factor. Repeated decimal. Express this as fraction. Okay, again, this is another type of problem in high school. All right, so let's see this one here. Let me just write down this parentheses so that's may make it easier. All right, so this is a there plus 0 times this one means that 0, 0, 0. Okay, so 3 zeros there. You see the patterns? Okay. This 3, 0 means times 10 to the there. Okay. So here we have 10 to the here 3, 3, negative 6. There. The next one, if you dare to guess. Okay. So you see this has a like this. This is A. Take that out. Factor this out. What's left is 1. This is 3 minus 6 minus 9. Okay. So this gives you R equals, the ratio is okay. So you know that the formula, the limit. This goes to 1 over 1 minus, this is the 3, right? So this is, what do you call it? What is this? 0.9. There. So it is 999 over 1,000. Okay, and you can compute this one. So this 1,000 over 999 times. Okay. So this is 1. So 1,000 times this. There. So the repeated decimals is nothing but that's as a fraction. Okay, questions? What we call a what you call a geometric series. Okay, let's see. Other is what we call a, what about this one here? The series is, if you look at the partial sums, S is just, Sn is just addition of 1, 2, just n, right? So adding, let me write this down. Adding 1, n times. So that's just n, all right? So Sn is, just gets bigger, and it diverges. So the question is, because limit Sn n goes to infinity is there. All right. What about this one? 1 minus 1 plus 1 minus 1 plus 1. There. All right. So if you write this down in terms of sigma notations, so this is k from 1 to infinity. This is negative 1 to the start from 0. Okay, so you get just a alternating alternating sign. So how is this a convergence? Because well, you have one, you subtract one, so that's it gives you 0. This always 0 also. If you think about pairwise, this 0, this 0, next 0, 0. This uh, is it correct that this should be 0? Should be 0. There's questions. All right. But if you think in terms of partial sums, you see partial sums. S0 is just 1. Okay. S1 is just 0. Okay. Because you subtract 1. S2 is you add 1 again. 1. And then subtract 1. 0. Right? And it keeps going on. So what you get is the sequence looks like this one. 1 0 1 0 1 0. Right? So it has no definite number that it's getting approached to, gets close to. So this is divergent sequence. Therefore, it's divergent. Okay. All right. We have a answer test for divergence. Okay. So that's easy. We know that if the series convergent, then an this limit must be 0. Okay. So the contributions from the terms farther to the right is small. So this tends to 0. Okay. So equivalency, this is if then statement. If this, then this one. So what's a statement equivalent to this one is if this is not true, then this is not true. All right. So that says if we find that this limit of these the terms is not 0, then the series divergent. Okay. Just this. Let me write this down. It's yes. Okay. So if you have a sequence, say from 0, doesn't matter. Okay. You can split this up to till some numbers there. This is partial sum. plus the additions. I would say this is the tail of the series. All right. You see that this if you take the if n goes to infinity, uh, so in order to make the series converge, then this tail of the series, the tail must be smaller and smaller. Okay? That means this one is the limit. If n goes to infinity, must be smaller. Okay, that means so 8k must be, let's say this one. Uh, okay, so let's write this statement here. Okay, so this answer uh, if the series converges, then this limit is 0. Or equivalently, if the non-zero, then the series divergent. Just one example. Just go quickly. Uh, I think this one. Yeah, looks like this one. Okay, so this is our 8K, AN in this case. All right, but you see that this one here, limit of AN is just this limit. This is just one. Then it's not 0. Okay, so what can we say is that then uh, just let me just show you this one here. All right, this example. Can you see this one? The sigma of this one, this polynomial, over polynomial. So the numerators n cube, denominators 3n cube plus 2n square. Okay, so this is our an. Okay, and if you compute the limit of an, you see this is just 1/3, and this is non-zero. So that's by the nth term test. This should diverge. Okay. All right, we'll stop here. And uh, I guess on Thursday, I'd like to have an hour of lecture and then followed by the problem sessions. Problem sessions, especially on this series, the beginning of the sequencing series. Okay, questions? If not, then I'll stop the